This lecture is on chapter 5.1 on Vsepr model and 3D geometric shape of molecules. So we know how atoms form bonds to create molecules, but what 3D orientation do the molecules adopt? So the 3D orientation of molecules is incredibly important for many different reasons. So for example, let's think about water. Okay, so we'll show you today that water actually takes up a bent shape instead of a linear shape. So writing up on the board so you can see this here. So a bent shape has a 3D geometry where you have an oxygen bound to two hydrogens, and it has a approximately 109-degree angle between the hydrogen, oxygen, and the other hydrogen. And it has that shape, even though we would expect possibly that this water could be linear with 180 degrees between. Okay, so this bent orientation here for water actually is entirely critical to the function of water itself. So the bent shape of water creates a polar molecule, which means that water basically acts as a magnet, where it has a negative portion and a positive portion. And so this allows water to dissolve polar molecules, such as salts, sugars, etc. And so living organisms are powered by the movement of salt and sugar. So if water would be that linear 180-degree orientation, it would mean it would not be polar, which mean it would not be able to dissolve salts and sugars, and it would not be able to power life as we know it on Earth. And so the 3D orientation of a molecule, such as our most simple molecule of H2O, is entirely critical to function. So it's important that we understand the 3D structure of all of these molecules. Another example is talking about the active site of enzymes. And so enzymes are, it's another word for a protein. And so what these enzymes do is they will convert a certain target molecule into something else. So basically, it's a catalyst that induces a chemical change. Okay, and so in an enzyme, there's what's called an active site or an active pocket, where the molecule is able to diffuse in, and then it locks into place, and then the chemical transformation occurs, and then that product then is allowed to escape out of that pocket. And so only the proper 3D orientation of a molecule will be able to fit inside of that active site of an enzyme. And so this sort of 3D lock and key formation allows us the chemical selectivity in order for the specific enzymes that drive biological function to actually work. So I encourage you to watch this YouTube video the video starts at 225 is what I'd like you to watch. And so this is showing a molecule entering the active site and going through a transformation. So these are just two of the many, many, many examples of how the 3D orientation of molecules is critical. So the VSEPR or Vsepr model is the theory that underlies our determination of the molecular shape of molecules, the 3D geometry of molecules. So VSEPR stands for Valence Shell Electron Pair Repulsion Model. And so electrons in bonds and in lone pairs occupy what are called, quote, charge clouds or regions of electron density. And so these charge clouds orient in a 3D positioning so that the electrons are as far apart as possible. So if you're working from an electron dot structure, you count the number of these, quote, charge clouds, so either the lone pairs or bonds, and then determine the molecular shape. Okay, so this will become more clear as we go through all of our different examples. Okay, the first case that we're going to be talking about here is for two charge clouds. So we can see here that for example, we have carbon dioxide, and then we have cyanic acid here. And so a hydrogen and a cyanide here. And so we can see that all of these are taking this linear sort of formation, and they have two charged clouds. So what that charged clouds means is that you have two different regions of electron density. There are no lone pairs around this central atom, just two sections of bonds. So even though this is a double bond, that's still a single charged cloud. So one charged cloud, two charged cloud. Even though this is a triple bond, it's a single charge cloud, single bond, single charge cloud. So we can look, so we're talking about how many charged clouds are around the central atom. So the central atom has two each, and that is a linear shape with 180 degrees. So we'll have to draw each of these molecules. You'll have to be able to draw each of these molecules in 3D shape. So the way that we draw a linear molecule is you have your central atom, and you simply just draw it in a linear shape with a 180-degree difference between the two. All right, so that's called linear. All right, next, three charged clouds. And so we can see here, these are examples of three charged clouds. And so again here, we can have either three separate sections of bonds. So 1, 2, 3 charged clouds around the central atom. Or it can be two sets of bonds, so a double bond and a single bond, and then a lone pair. So remember, those lone pair also count as a charged cloud as well. So both of these molecules here exist with three charged clouds. Okay? And so what we have here is what's called the parent geometry and then the daughter geometry. Okay, so the parent geometry is how many total charged clouds that we see. So both of these here, whether we have three bonds or we have two bonds and one lone pair, carry a trigonal planar parent geometry. But the actual 3D shape, the daughter geometry, is talking about just what chemical bonds are actually present. Okay, so if we go up and take a look at our drawing here, so for our three charged clouds, we have a central atom, and then we have three atoms extending off from there. And so all three of these atoms are in a plane, and they all have 120 degrees between each set of three atoms. Okay, and so this shape is called trigonal planar. So that is the trigonal planar parent geometry. Okay, and so if we put this trigonal planar, if we pick it up and put it on its side, we would see that it's all in a plane. So if we rotated this 90 degrees, we would see our central atom, and we would see just a shape that looks like that, 180 degrees. Okay, knowing that there's another atom that goes straight into the board. Okay, so when we get into class and for next lecture, we're going to work with some actual 3D ball and stick model simulation, so you'll be able to actually visualize this trigonal planar a little better. Okay, so this shape is called trigonal planar. So when we have bonds associated with each one, as we show here on the top for the COH2, we can see that on the slide, the COH2, we can see that that has a trigonal planar daughter geometry, the 3D shape. So if instead now, if we replace one of these chemical bonds with a lone pair, so for example, down at the bottom, the SO2, or also for other molecules as well, if we take our sulfur, we have an oxygen, another oxygen, and then we have a lone pair here. So any lone pair we draw with a little circle around it to draw attention to it. So when we're talking about our daughter geometry here, or an actual 3D shape of our molecule, we don't consider the lone pair. So that lone pair we can sort of cover up with our hand, and we can see that we now have this shape that's called bent. Okay, and so this same 120-degree angle exists between all of our charged clouds still. So we have 120 degrees here, 120 degrees here, and 120 degrees here. So if we ask you what is the angle If we ask you what is the angle between our oxygen, sulfur, and oxygen for this trigonal planar bent species, the answer would be 120 degrees. Okay, so those were the two for the three charge cloud. Next, we talk about four charge clouds. So this would be if you have a central atom, and then we have four different bonds or lone pairs surrounding. So this shape is what's called tetrahedral. And so here we're going to have to get a little more creative with the way that we draw. So if we have our central atom, in the plane of the board is drawn as solid lines. Okay, so we have one bond up in the plane of the board, one bond coming out in the plane of the board. And then we have to have an orientation talking about going into the board and out of the board. So the bond going into the board, we're going to draw that as a dashed line. And then a bond coming out of the board, we're going to draw as a wedge. Okay, so we have four individual charge clouds here. Again, when we get into class, you're actually going to be able to manipulate some models to see more clearly what this looks like. So we have two different bonds in the plane of the board, one bond coming out, one bond going in. And again, this is a tetrahedral shape. So tetrahedral parent geometry. So now what happens if we actually start to remove these individual bonds with lone pairs? Okay, so if all four of these are bonds, it's called tetrahedral. The same as the daughter geometry is the same as the parent, as always. And then so now, for example, for NH3, which is ammonia, if we have nitrogen, we have a hydrogen, a wedge coming out for another hydrogen, a dashed line for another hydrogen, and then we have a lone pair that's in the plane of the board. So now we have each of these three here. And again, we don't look at lone pairs for our geometry. I could probably draw this a little better for you guys. My apologies. To kind of illustrate the shape. Okay, so all these are sort of on the bottom. So this shape here is what's called trigonal pyramidal. Okay, so trigonal means a three-sided pyramid. So if we take a look here, we have 1, 2, 3 sides of a pyramid shape. So that's trigonal pyramidal. Okay, and then lastly, what if we replace two of our charge clouds? So this brings in water. So if we have water, if we have one lone pair on the top, another lone pair going into the board, a lone pair coming out, and a lone pair, a hydrogen coming out, and then a hydrogen in the plane of the board. Okay, so again, we don't consider these lone pairs when we're determining the actual shape. What we have here is another bent angle. So we write this here as bent. Okay, so let's take a look here at the bond angle between each of these individual daughter structures of the tetrahedral parent structure. So for the tetrahedral, where all of them are bonds, all of these bond angles are equal to 109.5 degrees. Okay? Whereas these guys here for the trigonal pyramidal, these hydrogen-nitrogen-hydrogen bond angles are equal to 107 degrees. And this bond angle between our bent structure, the hydrogen-oxygen-hydrogen, is equal to 104.5 degrees. Okay, so what we're seeing here is the more lone pairs that we substitute into this parent structure, the more that this bond angle is compressed. So what's the reason for this? So the reason for this is, if we think about where the electrons actually are in a bond as opposed to where electrons are in a lone pair. So if you have two electrons that are tied up into a chemical covalent bond, those electrons are going to be retained pretty well in space between the two atoms. Whereas if you have a lone pair of electrons, they are free to spread out as far apart as they want. So what we have here are these lone pair electrons are going to take up more space. So these electrons want to be as far away as possible from the other electrons. Because remember, all these negative charge electrons cancel each other out. So these lone pair electrons here are going to spread out more than if they were in a chemical bond, which has the effect of compressing all the other bonds. So for the bent structure, having two separate lone pairs, that has two different sections that are going to really spread out, which is going to compress the angle even more. So you're going to need to know these bond angles, the 109.5, 107, and 104.5 for tetrahedral, trigonal pyramidal, and bent respectively. And so you should be able to diagnose the difference and the bond angle to discriminate between a bent molecule coming from a trigonal planar, three charge cloud parent geometry, and a bent molecule coming from a tetrahedral, four charge density um, tetrahedral parent geometry. All right, next is our five charge clouds. So here we're talking about an expanded octet sort of molecule. All right, so for this here, we have our central atom. We have an atom coming straight up in the plane of the board, coming straight down the plane of the board. And then in the middle, we have one in the plane of the board, one going into the board, and one here coming out of the board. So what we have here is two different positions here, an equatorial position, which is along this central axis. So you can picture this as a spinning, you can spin these three in an angle, or you can talk about these three atoms, which is considered in the axial position. And this overall parent geometry here is called the Trigonal Bipyramidal. Okay, so the trigonal bipyramidal, again, so we have a three-sided bipyramid, so three-sided two pyramids. So we can see there's a pyramid here on the top, and then a pyramid here on the bottom, each with three sides. Okay, and so we have two different sets of angles here that we observe for our trigonal bipyramidal. So the angle between the axial and the equatorial, this angle here is 90 degrees. Same here on the bottom, 90-degree angle. And then the angle between our axial positions are 120 degrees. So it's the same, so this equatorial position here is the same as a trigonal planar. So if we tip this guy 90 degrees on its side and look straight down the barrel, you're going to see a central atom, and it's going to look exactly like our trigonal planar with 120 degrees in between each one. Okay, knowing that the axial now is coming in and out of the board. All right, so that's the trigonal planar five charge cloud parent geometry. Okay, so if we have bonds associated with each one of these charge clouds, that would mean that the shape would be just the same as the parent, as always. It would be called trigonal bipyramidal. Next, what if we replace one of these guys with a charged cloud? So with a lone pair of electrons. So those lone pair of electrons are going to substitute themselves in the place where they have the most room to spread out. So if we take a look at our bond angles here, we see the axial is only 90 degrees away from three other atoms. Whereas if you substitute those lone pair in the equatorial position, they'll be 120 degrees away from their neighbors. So there's much more room for electrons to spread out if they substitute equatorially than if they substitute axially. So lone pairs always substitute in the equatorial position for trigonal bipyramidal parent geometry. Okay, so that's very important. Okay, so let's take a look at this first substitution of one set of lone pairs into our equatorial position. So for example, we have our SF4. So we have our sulfur atom in the center. We have our fluorine in the top, fluorine in the bottom in the axial position. And then equatorially, going into the board, we have a fluorine. Coming out of the board here, we have a fluorine. And then we're going to have this lone pair here in the plane of the board. And so what we've got here is what's called a seesaw position. And so this seesaw position, if we turn it on its side, we can see that it is really, if we just flip it on its side here, it looks like a seesaw. Okay? So if we take a look at our bond angles here, this lone pair is not going to affect the bond angle between the fluorine and the sulfur, so that's still going to be 120 degrees. But it is going to slightly push this 90-degree angle here, which means that this angle between the fluorine and the fluorine, sulfur, and the other fluorine is going to be slightly less than 90 degrees. So if we were to truly draw this in a representative structure, we would draw these bonds slightly crooked, so slightly displaced. Okay, and again, this is called seesaw. Okay, next, what if we replace two charge clouds with lone pair electrons? So again, both of these are going to locate themselves equatorially. So for example, here we have ClF3. So we have our chlorine, we have our fluorine on the top, fluorine on the bottom axially. We'll include our other fluorine here, and then the other two positions equatorially are going to be our lone pairs. So what we're going to see now is if we're taking a look at, so again, this is called T-shaped. Okay, if we turn this guy on the side, you can see if we flip it over, it has a T shape. So chlorine, fluorine, 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 with our two lone pairs coming out of the top. All right, so T-shaped. And again here, we're going to see that these two lone pairs are also going to deflect these fluorine atoms away. And so what you're going to get again here is an angle less than 90 degrees now. Excuse me. Less than 90 degrees between our axial and equatorial axis. Okay, so if we were to draw this a little more representative of true nature, we would show a deflection of those fluorine atoms. Okay, so that is T-shaped. Next, if we are going to substitute three sets of lone pairs onto our 5 charge cloud parent compound, for example, I3, we have our central atom, and we have both of our atoms connected axially, and then we have a lone pair in all three positions equatorially. And so what we're left with now is 180 degrees between just the axial axis here. And again, this is linear. Okay, that was for 5 charge clouds. Finally, let's take a look at 6 charge clouds. So again, this is an expanded octet situation here. And so what we have here, the way we draw this, we have our central atom, axially go up, axial go down, and then equatorially, what we have here is molecule going in the board, coming out, in the board, and coming out, all in that level plane here in the middle. And so this parent geometry with 6 charged clouds is called octahedral. And so if we turn this on its side, we can see, so if we rotate 90 degrees, we'd have our central atom, and then we could draw all on the plane of the board here. You could see that we are forming that sort of diamond shape or a square, whichever way you orient. Okay, so we have an octahedral, so an 8-sided shape. Octa means 8, so 8-sided shape. And so for octahedral, whether you're axial or equatorial, all of the angles in octahedral are all 90 degrees apart. So there's no real differentiation between axial or equatorial for octahedral. So there's no specific classification. All right, so if we assign chemical bonds, so all 6 of these charged clouds, the daughter shape or the 3D geometry would be called octahedral, as expected. Next, what if we substitute one lone pair for one of these charged clouds in the octahedral parent geometry? So what you're going to get is, for example, SbCl5. We have our central atom. And so we're just going to draw these lone pairs in the axial position. So we have our lone pair shown here at the bottom. And then in the center, we have our 4 chlorines and then the 1 axial chlorine on top. And so this lone pair here is going to push that angle slightly. And so what you're going to get is a slightly less than 90-degree angle between this axial and equatorial position for these shapes. And this is what's called a square pyramidal. Okay, and so the reason this is called square pyramidal, if we turn this on its side, we would see that it has that square shape on the bottom, but it is going to make a pyramid. So square pyramidal. Okay, the final shape that we'll show you today is if we substitute 2 different lone pairs into this octahedral parent geometry. And for example, here is XeF4. So we have our xenon here in the center. We have our fluorines coming in our quote unquote equatorial position. And we have lone pairs on the top and the bottom. And so these lone pairs are going to equally push on these fluorine atoms, so there's not going to be any deflection in the angle. And all we're going to see here is 90-degree angles between all of these individual sets of 3 atoms. And so here we have called square planar. All right, and if we look on the side here, it's all the way in a plane, just like trigonal planar. If we take a look down the side, we see it's a total plane. And if we turn it up on its side, we would see that square shape. Okay, so again, we will, over the next couple classes, we're going to work to get yourselves familiarized a little more with these individual shapes. And we have a worksheet here for you to practice drawing all of them. So this slide here and the next slide is just sort of a review of all of the different parent geometries and then each individual daughter geometry or the final 3D molecular shape that you'll see for each different type of molecule. And then it provides an example for you as well. So there's no substitution for actually putting the pen to paper and practicing. So because of that, we have a worksheet for you to work through. And the other sort of key aspect here that I think I neglected to mention earlier, doing these drawings entirely requires you to complete a proper Lewis structure. If you can't draw a Lewis structure correctly, then there's no way that you can follow the VSEPR theory correctly. So you need to be able to correctly identify when an octet can be expanded, when it cannot be expanded, et cetera, to be able to draw and correct Lewis structure and assign the correct number of lone pair electrons to both the central and terminal atoms. So the first part of this VSEPR worksheet is to have you work through a bunch more Lewis structures. And then once you've identified the proper Lewis structure, then you can go on to solving these proper 3D structures. All right, that's it for today. Thank you.